The first presentation will be regarding the topic of biogas upgrading into biomethane, and will be presented by Grigoris Pantoleontos from ZEOCA 3D project, affiliated with the Center of Research and Technology CERTH in Thessaloniki, Greece. He is here today, so I invite him to prepare to enter the stage. Meanwhile, we should know about Grigoris that he has been participating to numerous research projects, and his work includes experiment design and optimization of membrane-based processes and the techno-economic evaluation of these novel technologies, strategic planning and optimization of technologies. The title of his research result today is Biogas Upgrading Using a Gas-Liquid Contact Membrane Process, Modeling, Simulation, and Membrane Wetting Estimation. I'm leaving the floor to you. Thank you.
Thank you. Good afternoon. We are from CERTH, Center for Research and Technology of Thessaloniki, Greece, and we're about to present a study on biogas upgrading using a gas-liquid contact membrane process, and we are focusing on the modeling, simulation, and membrane wetting estimation. Here's an outline of the presentation. We present the aims of our study. We proceed to the modeling of the membrane-based gas absorption process, other isothermal operation, the formulations in the fiber in the cell side, and the boundary conditions. We have included all relevant mass transfer resistances and a reaction rate term in the cell side between carbon dioxide and the amine. We have found that the ethanol amine is the most appropriate for our study for this kind of processes. We proceed to results, what we can achieve in terms of carbon dioxide removal. The membrane wetting estimation, we will do a parametric analysis on the cell side mass transfer correlation, and we will present a computational exercise for dynamic response of the system when disturbed after reaching a steady state, and the conclusions. Although the conventional gas absorption processes such as packed towers, packed columns are the workhorse of chemical engineering industrial processes over the years, there are still shortcomings that can be overcome by introducing a hybrid process, an intensified process, which combines the advantages of a gas-liquid reactive process and mesoporous membranes. For example, we know before the contact surface area, we have a compact system with a very high specific surface area. For example, in this project, we were using a commercial 3M liquid cell mini module, which has more than 7,000 hollow fibers, offering a specific surface area of 3,600 inverse meters, which is at least 4 times that of a conventional equipment. What we're trying to do here, we have a biogas feed, a binary biogas feed of methane and carbon dioxide, 60-40. We're feeding it in the hollow fiber side, and we have a solvent of an aqueous solution of the ethanol amine. We have found it's the most appropriate in this study, flowing outside of the fibers countercurrently to the fiber's flow, and we need to remove carbon dioxide into the solvent and have biomethane almost intact, having not lost in the solvent, that is ending up with high concentration at the exit of the fibers. Here is the model. We're modeling a single hollow fiber, assuming that we have an equal distribution of biogas into the whole bunch of fibers. We are solving, we have a mass continuity equation, a symmetry boundary condition, and we need in countercurrent mode 1D model, 1D mass transfer equation in the cell side, which includes the reaction rate between carbon dioxide and the ethylamine. Now, if we have no variation of the diffusing component in the cell side, so we need to solve only the hollow fiber side, we have developed an analytical solution, and we are published it in open access journal in the course of ZeoCAD 3D project, using open source software such as SageMath and commercial one in Maple, so that anyone can find the scripts and run a simplified case of a linear boundary with a linear boundary condition and only solving the hollow fiber side. But this is not the case for this study. We need to incorporate the cell side mass transfer conservation equation, and we are coupling the two computational compartments with a linear boundary condition, which postulates that the mass flux at the inner wall of the fiber is equal with the Kx, a combined mass transfer coefficient, multiplied with the concentration difference at the outer parts of the membrane. This is the most crucial equation in our analysis. The inverse Kx value is the overall resistance, and we are resolving the overall resistance into its constituent parts. The last part is the cell side mass transfer resistance, which incorporates KSO, which is a mass transfer coefficient in the cell side found by physical absorption cases. It is enhanced E times because of the reactive conditions between carbon dioxide and the ethylamine. For the membrane part, we have included a term, the wetting, that is, we are assuming that we have a resistance in series. First, the gas has to overcome the resistance of the gas-filled part of the pores, and then to overcome the resistance imposed by liquid penetrating into a part of the pore that we need to find. The notion of a partially weighted mode of operation stems from the fact that there is a discrepancy between the experimental results and the so far developed mass transfer models and correlations. We need to put something, a parameter that has a physical meaning in the membrane equations that slows down mass transfer. So what we were doing is to find the wetting values for each experimental set, which matches so that the experimental data are matched with the developed model. We're using an overall reaction rate of third order between carbon dioxide and ethylamine, found by literature, it is by Chiquita. And as a base case, we're using cell-side mass transfer correlation by Costello, and we're doing a parametric analysis on this. For this equation-based model, we need an equation-based software, and gPROMS is fine for this. It's excellent for this type of processes. Here is what we've done in the experiments. We are using an aqueous solution of the ethylamine of mild concentration, 0.25 molarity. For this bunch of experimental data, we have developed a correlation for to predict carbon dioxide removal based on this data, which is correlated in terms of widely used dimensionless numbers widely used in the membrane modeling canon, such as the inverse Gratz number, which depends on the velocity in the fibers, and the gas to liquid flow rate ratio, which depends also on the flow rate of the liquid in the cell side. So we have a correlation with respect to both flow rates in the cell side and in the gas side. This is statistically correct. It does not have very many degrees of freedom, but it serves us well for experiment design, provided that we're using this concentration of the ethylamine and these ranges of, we are within the ranges of gas and liquid flow rates. From the graph, we can see that we can have a very efficient process for removing carbon dioxide first. We can have more than 95% of removal, having highly enough gas to liquid flow rate ratio of almost 7.5 or less. And the second important thing is that based on the experimental measurements and the model, the mass balance calculations, there is negligible diffusion of methane into the liquid. So using this technology, we can have the highest possible recovery of methane, almost 100%, and highly concentrated we may have of methane because we have removed most or all carbon dioxide. This is the main result of our study. In the y-axis, we have the wetting values. The x-axis, we have the liquid flow rate. We have 9 experimental sets. We order them in terms of the Z star, the inverse Gratz number. Now, forget for a moment the large values of wetting. The first wetting pattern we may discern is that for the same liquid flow rate, the wetting values are concentrated close to each other. And this is the decisive factor to verify our model. Because intuitively, we expect that for the same liquid flow rate, we should have the same wetting. The large values of the wetting may be attributed to the incorporation of the enhancement factor also in the liquid filled part of the pores. And this is what the theory says, that since we have gas-liquid contact, even in the membrane pores, we should have an enhancement to mass transfer. But the problem is that we might not have the same mass transfer mechanism in the liquid bulk, cell side, and the membrane pores. So, by incorporating the enhancement factor E in the liquid filled parts of the pores, it is in the denominator so that the resistance decreases. The wetting value should be high to catch up with the incorporation of the enhancement factor. In the next months, we will do a parametric analysis of enhancement factor in the membrane pores to see what happens. The second wetting pattern is that by increasing liquid flow rate, we see that the wetting decreases. And this is something we also noticed in a relevant publication in Canadian Journal of Chemical Engineering in 2017, when assessing a physical absorption case. And this observation may be an explanation, might be that by increasing liquid flow rate in the cell side, increasing liquid velocity, that is, we have smaller residence time of a mean residence time of a fluid element to remain in the cell side and cause wetting. Here is a parametric analysis of the cell side mass transfer correlation. We know from the literature that the cell side mass transfer correlation values range a lot. We don't know actually this value. The KSO value refers to the physical absorption case before enhancement, before applying the reactive conditions. And we're introducing an averaged K external value, an averaged combined mass transfer coefficient. And we see that regardless of the x-axis, we have the times multiplying the KSO value. Regardless of the value of KSO, the K external value remains the same. Now, what's that? In the graph, we're showing a reference case, which is almost the same for all experimental sets. This is the asymptotic enhancement factor, the Hatta number, and the actual enhancement factor. These are values used in the reaction engineering. And we count from right to left because we have a countercurrent mode of operation and the enhancement factors are higher the right. We see that the Hatta number and E are almost equal in the whole length of the cell. And in this case, the corresponding expressions say that the apparent cell side mass transfer correlation value, Ks, is independent of the flow conditions, is independent of the velocity in the cell side. So with this observation, which is valid for all experimental sets, we can have a say on the experiment design by a single pair of Z star and M star. And a reminder, working on this within this region, when the Hatta number is almost equal to the enhancement factor, is convenient when one needs to derive intrinsic reaction rates, that is, by definition, independent of the process flow, of the process from independent of the flow rates in the cell side. Now, here's the last slide. This is a computational exercise based on the previous. We have solved the system. We have a reference case of the first experimental set. We see that Y out old is the molar fraction of carbon dioxide at the exit of the fibers. It is less than 0.40 as was the feed, because we have removed carbon dioxide. And it drops to 0.09. This is what we solved. This is the steady state solution. Now, we know that biogas composition may vary not only seasonally, but in the same day. So what we do is impose a new biogas feed composition from 0.41 to 0.45 for some reason. And we impose a step change. Suddenly, this inlet composition changes. The new molar fraction of carbon dioxide at the exit is 0.1194, more than the previous exit composition of carbon dioxide. And this is because I forgot to tell you, we retain the same liquid flow rate. So we play with the composition, but we retain the same liquid flow rate. And what we expect from the previous analysis is that since we have the same liquid flow rate, we expect that we have the same wetting. So we switch from a matching case to find the wetting value to a simulation case. Set the previous wetting value to this simulation case and calculate the new molar fraction of carbon dioxide at the exit. The new molar fraction of carbon dioxide at the exit is more than the previous one. And this is obvious because we have the same liquid flow rate and cannot accommodate more carbon dioxide entering the system. So we end up to a higher composition of carbon dioxide at the exit. And we see also that the response of the system is very fast. We have the new steady state reached after 2 minutes of operation. And this is something we've seen in the measuring equipment. When we alter something, anything, we almost saw that immediately in the analyzer, that something has changed after 2 minutes or so. To sum up, we believe that we presented a mass transfer model of sufficient fidelity using a 2D formulation of the fiber, 1D in the cell side, including all relevant mass transfer resistances. The process is very efficient. We can gain high carbon dioxide removal and recovering most biomethane from the initial mixtures. We have identified 2 wetting patterns. The wetting depends mainly on the liquid flow rate, and that the relative contribution of the liquid filled part of the membrane resistance decreases for higher flow rates. And for the parametric analysis, it affects the wetting computational estimation, and we see that something that can be used also for experiment design, that the observable cell side mass transfer coefficient and the K external, the overall mass transfer coefficient, mainly depend on the reactive conditions. We did a dynamic analysis to show how this can be used in dynamic simulation. And we have a very fast response of the system, which is almost 2 minutes. And for example, larger modules, which is 2 times that of a mini module, we expect that the response of the system might also be very fast, not 2 minutes, but very, very fast. That's all from my side. Thank you for your attention.
Thank you very much.
before leaving the stage, I have an open question for you. Apart from DEA, which other amines have you used?
During the project, we have experimented with the pure water, which does not give, because it's mainly a physical absorption case, we didn't get any meaningful carbon dioxide removal values. We have used monoethanolamine and methyldiethanolamine as we have seen that monoethanolamine has an irreversible effect on the membranes, which is also mentioned in a couple of publications. And methyldiethanolamine is not so, does not have the capacity of diethanolamine to absorb carbon dioxide. So we ended up using diethanolamine.
Thank you again. Do we have any open questions from our meeting here? It seems there are no further questions. So thank you for your time and for sharing your work, to you and to Mr. Dimitri Koutonikolaou.